intro to acids and bases. To acids and bases. Number one, acids and bases are important because they are everywhere, every day. From cleaning supplies to regular life, just life in general, life in your stomach, life in your body, life in a pool, the food you eat, the makeup or not makeup that you wear, the sweat that you produce. Maintaining a good pH balance is a super big thing in everyday life. There's pH balanced makeup, pH balanced detergent, pH balanced toothpaste, pH balanced everything. So pH balance is huge for everywhere and everyday life. So the concept of acids in everyday life are just so radically important. Now, in chemistry, they're important because there are acid-base reactions. There are redox reactions. As you'll discover later, when electrons are transferred, that is an acid-base reaction. A lot of the stuff in the lab has to do with acid-base titrations. And titrations is another way to discover the concentration or molarity. These brackets right here are another way to say concentration. So is molarity. Molarity is another way to discover the concentration of an acid or a base. And so acid bases are important as far as just life in general, chemistry. A lot of the reactions in the lab have to do with acid-base reactions. When statues corrode, or when tops of buildings that were brass get moldy looking green, that is acid-base reaction from the H2SO4 that is falling from the sky. That is sulfuric acid. So they are just radically important, acids and bases. Nobody, and I'll put this in red, nobody I've ever really talked to has liked acid-base reactions, because as you'll see later, as we get into the calculation portion of it, it's going to get a little intense. So let's move on. There are three basic definitions of acids and bases. One is going to be the Arrhenius definition. The next one is going to be the Bronsted. I haven't figured out how to do that on a computer yet, so that line through the circle, Bronsted-Lowry definition, and then finally the Lewis definition. So let's define these. Arrhenius says that an acid produces or raises the concentration of H plus ions, and that a base raises or produces the concentration of the OH ion in solution. Bronsted-Lowry says that an acid is a proton donor, and a base is a acceptor. Lewis at that point said that an acid is an electron acceptor. Make sure that you see the difference there. An electron acceptor, and then a base is an electron donator. So there's a couple differences between Lewis's definition and Arrhenius, as well as Bronsted-Lowry, and we'll talk about that further in coming videos. So there are three major points there in, or three major definitions there in our intro to acids. So let me just say this right now. For Arrhenius and Bronsted-Lowry, they are concerned with solutions mainly of water, H2O. But specifically Arrhenius is H2O prone. Bronsted-Lowry is okay with the water beaker, but he is also saying, what if you fill it with ammonia, NH3? What if you fill it with that? So Bronsted-Lowry, he could do either one of these, okay? But his whole idea was to take it out of just water. And then Lewis, Lewis Dot, he was interested in the transfer of electrons. And so he made it available to even take it out of solution. So you didn't necessarily have a solution. But one thing you need to remember is that when you're dealing with acids and water, that free hydrogen ions, if you put a hydrogen ion in here, it's not going to exist by itself. It's going to connect. No, same with over here. They're not going to connect, or they're not going to just remain free. So free hydrogen ions, let me write that down. Free hydrogen ions do not exist specifically in water, okay? I don't want you to apply that to this completely, but just know that it does apply to this completely. So those are our definitions. Those are how we are basically going to view the acids and bases. And there were some limitations to each of these. Specifically, the Arrhenius was only water. Bronsted-Lowry was still only solution. And so there was a need to take it outside, because you could see acids at work in nature outside of solution. So let's move on and let's do some acid-base comparison. So acids, and let's make bases in blue because it just seems to fit every once in a while. Acids and bases. So let's say this, acids and bases. So acids are, they have a pH of less than 7. They are sour to taste. They burn, and they are usually sticky. Bases have, and let me put pH out here. pH. We'll talk about that in just a minute. And then they taste. Then they feel. And then they feel sticky. Bases are generally, bases are always pH greater than 7. They are bitter to taste. Who did this? I don't know. They're odorless. Now they can also, except for ammonia. Ammonia has a smell, terrible too. NH3. So I don't know how they figured out that they were sour. I can figure out how they noticed that they burned and were sticky, but who tasted this stuff? I don't know. For the sake of science, people have given up stuff so much. So slippery are bases, slippery. When you think of bases, you can think of cleaners or soaps. When you think of acid, obviously you can think of stomach acid, battery acid, pool acid. So those are some basic comparisons. Specifically, I want you to remember these for our next videos coming up. pH. And so those are a few comparisons with acids and bases. So let's move on. And acids and bases are placed on, and let's do this since we're right there. They are rated, or their strength is identified by something called the pH scale. pH scale. Now the pH scale is a logarithmic scale, and particularly it is a log 10 scale, which means that every number increases by 10, and we'll talk about that in just a little bit. The pH scale goes from acids being the lowest number, and then the bases being highest number, and we'll put out here number for both of these. Okay, so let's just look at that, the pH scale, and a lot of people do it up, and some people do it sideways. We're going to do it sideways here for space. And so what you would do is basically you would see a line, boom. And on that line, you would see numbers written. So I have spatial issues. So let's make the acids in red. 0, 1, 2, 3, 4, 5, 6. And then we'll make the neutral and 7 in white, and then you're going to make the bases 8, 9, 10, 11, 12, 13, 14. I did it. So these are acids, and these are your bases. Oops, sorry. These are your bases. And if you're looking at this, as you go up the scale, say for example, it's gonna increase as far as its basicity, or it's becoming more alkaline here in the middle. Okay, so the strongest acid is going to be, let's just say, one of the strongest acids, HCl, hydrochloric acid. That's going to be at the 0 point. The next strong acid is going to be, say, stomach acid. Now that stomach acid, because it is a log 10 scale, let's make that green. Now let's go back here, boom. Since it's a log 10 scale, stomach acid is going to be 10 times less. So this is going to be 10 times less acidic in nature. Acidic in nature. Okay, and as you keep going down, this is going to be 100 times, and then 1,000 times. So the log 10 scale makes recognizing acids and bases and doing calculations much easier. So I wanted to introduce you to the pH scale here. What we're going to be doing is we're going to be discovering the pH of various acids. And then the last thing I want to say is that there are strong acids that you need to memorize. So a strong acid would be considered HCl, H2SO4, which is sulfuric acid, hydroiodic acid, which is HI, hydrobromic acid, HBr, nitric acid, HNO3. That is a supremely strong acid. And then HClO4, perchlorous acid, my bad. These are your strong acids that you need to memorize. In fact, most of the questions that ask you to identify strong acids you're just going to need to memorize them. A lot of people think that hydrofluoric acid is a strong acid, and it's not. It is not a strong acid, and I would argue to say that it's not a strong acid because of the electronegativity of fluorine. Because remember, strong acids, strong acids break up or dissociate completely. And with that electronegativity of fluorine being so high, it makes it very difficult for it to break up completely. So hydrofluoric acid is not. But as you go down the list, hydrochloric acid becomes easier. So let's just say something, for example, like down here, and I went back up. This is going to be drain cleaner at 14. And you don't want to drink this stuff either. I mean, bases and acids are dangerous. This is going to be distilled water, not tap water. Why do you think it's not tap water? Because tap water contains other ions. So tap water is actually not neutral, but distilled water is neutral. Okay. And then, say, for example, soap is going to be about number 12. Soap is about number 12. Let's see, what else? Let's see, 5 is going to... my 5 is my favorite. Coffee. Coffee. And then, say, for example, like soda. So these are some basic general movements of what could be calculated, but as you see, it becomes less. So the acidity of this, actually, let's do it like this. So we're going to make this arrow do like this. We're going to do like this. And we're going to do like this. Nope. And do like this. It's patriotic acid pH scale. It's supposed to be an arrowhead. Boom, there. So the acidity decreases as numbers rise. Just remember that can be confusing because you're thinking about acids being strong and then the numbers getting big. So yeah, just think about that. Otherwise, that is your basic intro to acids and bases. You should have learned that they are important everywhere and in the chemistry lab and in our body. You should have learned that nobody really likes the study of acid bases because they're a little bit intricate. You should have learned the 3 basic definitions. You should have learned some differences between acids and bases. You should have learned that the pH scale is a logarithmic scale, meaning it increases by 10, multiply by 10 every time. So acids are the lowest number, bases are the highest number on the pH scale. The pH scale goes from 0 to 14, 7 being neutral. Acidity decreases as the number rises. You should have your strong acids there so that you can remember them, memorize them, and remember that strong acids, just like strong electrolytes, break up or dissociate completely in solution. So therefore, they are said to be ionized completely.